Yo, okay. So yesterday we made pickles and we started talking about chemistry and atoms and stuff. So today we're going to dive a little bit deeper into these atoms and we are going to identify what exactly they do and what they're made up of. So first of all, I'm going to help you out and calm your curious minds by telling you why I have a guy clad in blue and red spandex and a you know, sea green mullet. So anyway, back in the 80s, there was this cartoon called Captain Planet. And Captain Planet was this cheesy, environmentally conscious cartoon that had a bunch of different people shown below, here, here, and here. They would get together with their little rings, and they would come together whenever they had some environmental crisis that they couldn't deal with, and they'd put their rings together. And so they had all these cheesy motifs and powers like Earth and hearts. Somebody was heart. I can't remember. I think it was that chick. And then it was like fire and wind, and the list goes on. So what they did was they would come together, they'd conjure Captain Planet, and he would save the day. And so the reason I have this is that Captain Planet represents the big picture that is created from a lot of smaller things or people coming together. Okay, so only when they came together with the rings did Captain Planet show up. And that's what atoms and matter are for each other. The people in the background are the atoms, and when they come together, they can build virtually anything in the universe. So that's what they do. When atoms unite, they make matter. And so we are going to use a different example to kind of understand this concept. So yesterday I mentioned something about Legos, and so if you've ever played with Legos, chemistry is virtually taking a Lego set, building it together, and going back and finding those bricks and taking them apart and building something completely different. So if you decided to build a boat out of your Lego set, you could take it apart, and with those same pieces you could build a car. So two different things made out of the same pieces, and that's what atoms and matter are. So matter is basically any substance that has a mass. Okay, so if you can find the mass to it, you're looking at matter. And all matter is made up of atoms. Okay, there is this thing called antimatter for those of you who are kind of into that stuff, but we'll get to that later and we will discuss it. But the thing is, atoms are small units of what's called a chemical element. So to paraphrase this, an atom is basically a car. Okay, so if you go to the parking lot, you'll see a bunch of cars, but you'll see some Fords, you'll see some Chevys, you'll see some Hondas, you'll see some Volkswagens, BMWs, you get the picture. So cars have different brands, and so a different brand of an atom is called an element. And we might call that, instead of a Ford or a Chevy, nitrogen, or hydrogen, or phosphorus, or sulfur, or oxygen. So those element names are like brands of atoms. So that would have taken you on your comprehension sheet through about the first three questions, including actually the fourth, because we're kind of getting into elements here. So to get back into it, atoms are all a sort of element, but all atoms aren't the same element. So the thing is, you'll see down here that we got this in the background, this thing called the periodic table of elements. And it's got 118 elements. But each of those elements is a different brand of atom. Okay? So just like if we were to go out into the parking lot and look at a car and say it's got four wheels, it's got an engine, you'll find some common parts, right? And so just like a car, an atom, no matter what element or brand it is, it has common parts. So all atoms have at least one proton. They will have, that's nice, rhombus. And then we have some quantity of neutrons usually. Then atoms will have electrons. Now, the gist with an atom is that these two guys can vary, okay? So you can change the neutrons and the electrons, and it can still be the same element. But if you change the protons, you will change the element. So what does that mean? Let's do an example. If we go to the periodic table, okay, this is actually involving the three subatomic particles, which are the protons, neutrons, and electrons. You just don't necessarily see all of them. So the thing is that a proton has a positive charge, and an atom is always identified by the amount of positive protons it has inside of it. And it's as simple as finding the number on the periodic table. So for example, if you are an atom that has 1 proton, you are hydrogen every single time. So if you were to mess with that number of protons and add 2 to make a total of 3 protons, you are now called lithium, which is probably familiar to you because of lithium-ion batteries that power much of your electronics. And so the thing is that the atom or the element's identity or brand name is tied specifically to how many positive protons it has. Now, let's go back to our friend lithium. So let's draw a lithium atom, okay? A lithium's got to have those 3 positive protons. So I'm going to represent those guys with these little circles with a plus sign in them. There's our 3 protons and your lithium. Now, you're also going to have these neutrons. So let's use a different color. Let's use purple. That's fun. So we're going to have a neutron there, a neutron there, a neutron there, and a neutron there. Bam! Now, we're going to next do some electrons. And so I'm going to show electrons in green, and they got these little negative signs to show that they are negative. And we're going to put them around this cluster of protons and neutrons. So what's the deal here? You're lithium because, and only because, you've got 1, 2, 3 protons. Okay? Now, guess what? I'm going to mess with this lithium atom. Hooah! Okay, I took off an electron. Are you still lithium? Do you still have 3 protons? The answer is yes and yes. You're still lithium because, check, 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 you still have 3 protons. Well, what if I mess with the neutrons? Okay, guess what? You're still lithium. But what if I mess with the protons? And I add 1. Okay, so that means you now have 4 protons. So what are you? Crisis! Where are you? Oh, here we go. So you are now beryllium because you have 4 protons. Boom! So once you change the protons, you change the element. But that's the only thing that will change the element. Got it? Now, we're going to keep going. We are now going to look at specifically where these protons, neutrons, electrons are inside of the atom. Now, what's this slide saying here? It's reiterating or repeating much of the stuff I just talked about. So basically, if you change the protons, you change the element. There's not much more to it than that. By the way, there's 118 different varieties of proton counts in atoms, which means there's 118 elements. Now here's where we got to get into where's your protons, where's your neutrons, where's your electrons at. So you've got a little bit of a diagram in the back, okay? And you'll see that your protons are represented as blue spheres with pluses in them. Ah, ta-da, you got a proton, okay? Ooh, there's another one. Now, those are your protons, and they're in the center. That's the key. And they're not the only guys in the center. We also got neutrons. Well, bam! Shown as red blank circles. Neutron, neutron, neutron. So protons and neutrons like to hang out in the center, okay? They're very centered. They have a great awareness of who they are. Now, the electrons, on the other hand, don't like to hang out in the center. They like to hang out in orbit the cluster of protons and neutrons in the middle. So they like to stay on the outside, and the protons and the neutrons like to stay on the inside. And so what we call this region of protons and neutrons on the inside is called the nucleus. So if you've ever heard of an atom's nucleus, that is a cluster of protons and neutrons. The electrons stay on the outside. Why would they do this, by the way? Because a negative, if you remember magnetism, negatives and positives don't touch. They don't. So they repel. In a sense, they basically they can't geometrically come together. Okay. Now, when you get like charges and magnetism, they repel, right? So you would think, well, they're kind of attracted, and they kind of are. Otherwise, the electrons would just run off. But your positives in the nucleus keep the electrons roughly around, but they don't collide with them. okay? So they are separate regions. And why? The answer is basically you get into, quantum physics and stuff like that. So the gist is electrons go around the nucleus, and the nucleus consists of the protons and the neutrons. Now, about those protons and neutrons, okay, let's check it out. So you've got how many protons? Now, it says 6 here, but you can only see within the view 1, 2, 3, 4, which means there are 2 out of sight for you. Okay, this diagram isn't the best. I will not use something tricky like this very often. So there are 2 that are kind of out of sight here. So if you have 6 protons and we have apparently 6 neutrons, we got 1, 2, 3, 4, 5 in view, and there must be 1 out of the kind of away from us on the other side of the nucleus. These 2 numbers are important because they give you what the atom's mass is. So if I have 6 protons and 6 neutrons, this mass of the nucleus is 12. So you'll see mass numbers and you'll see atomic numbers. The atomic number is just the number of protons. But the mass number is the sum of the protons plus the neutrons. And so that may be a little confusing to get down, but we'll get used to it with a little bit of practice. Now, a couple last words. A lot of people, including our former president, George W. Bush, would say nucleus, or nuclear warfare. And guess what? That's not a word. Okay, don't say that. It's not a real word. You will be embarrassed by anyone with some sort of sense of diction. So it is nucleus. Don't forget it. It's eus, not us. Okay, it's not nucleus. Terrible. Don't say that. All right, so we're going to identify some elements here. This looks familiar from your Pickle Lab. So we got the atomic number. It's always at the top of the box in the periodic table. Atomic mass is always the decimal number at the bottom. Why is it a decimal? We'll get to that. The element name is, its location is actually usually under the symbol, but we'll get there. And then the symbol is the giant letter. Some of these guys have weird symbols. So like sodium. Element number 11, has a chemical symbol of Na. What's the deal? Okay, the thing is that sodium has an Na because Na is Latin for sodium. So Na is short for natrium. And so since Latin is basically the universal language for science, many of the early elements have Latin or Greek prefixes for their symbols, basically. So why did we do this? We were starting to run out of room. Sulfur was used for, say, an S was used for sulfur. So we had to come up with something else to represent sodium. So we used its Latin root or its Greek root. So that would be why some of them have weird symbols. So what do you need to know? You need to know protons are positive, neutrons are neutral, electrons are negative. These 2 guys hang out in the center of the atom, in the nucleus. These guys orbit it and go around it. An element is based on the number of protons it has. The mass number is the sum of all the stuff in the nucleus, that is protons plus neutrons. And then atoms make up basically everything. So what we're going to do next is get you guys started on your practice. So without further ado, I'm going to go ahead and switch over. So you'll see that today we have some protons, neutrons, electrons practice. So let's get started on it. You will have a square on the top, and it has a box from the periodic table, which I've also linked to your Canvas page. You'll see that the atomic number, or the number of protons, therefore the identity of the atom, is up at the top. So here we are looking at an atom with 8 protons. So we have basically an 8. So that means an atom with 8 protons is called oxygen because it's number 8. So the symbol would be a giant O. The name would be written here. And then the mass number is the decimal number, which can be either 15.99 or sometimes you'll see, I think, 16.01 for oxygen. And that's it. Okay? And remember, the mass number is the average of protons plus neutrons. So we'll get into the average stuff later. Now, what we have here is a chart where we're going to fill in the number of protons, neutrons, and electrons. So we got one done for us, so let's check out boron. Okay, boron is number 5 on the periodic table. Okay, so basically its symbol is a B. So when we look at it, we go back to our atoms notes and we scroll up a little bit. We go to the periodic table, we find boron, which is number 5. This is the guy we're talking about. Okay, because it's number 5, it's got 5 protons. Because it's got 5 protons, it's called boron, which is the name, and then the symbol is there. And then the mass number is out of view, but you can see it on your periodic table. So here's what we do. Boron, there's a symbol, it's B. Its atomic number is 5, number of protons. Here's the key. The atomic number is going to equal the number of protons. So these two columns should always be the same. Okay, this guy should be the same as that guy all the time. All right? And then the neutrons are going to be whatever the difference is between the mass number, which in all of these is going to be a whole number, and I'll explain why later, okay, on another day. But these are all whole numbers. These are not going to be decimals. And I'm going to actually give you the whole number masses for the elements at the bottom that don't have any. So because we have a mass number of 11, that means that in this atom, we have a cluster of 11 things in the middle. So that would include, if we drew a picture, 11 things. So this is the nucleus of the atom. 5 of those are protons. If we have a total of 11 things, that means we must have the remaining 6 as neutrons. 1, 2, 3, 4, 5, 6. So what you do is you take the mass, you subtract the protons from it, or the atomic number, which is the same thing, to get the neutrons. Electrons, for the sake of this activity, and do not get used to this, this is just for today, are going to also equal the protons. So let's do an example. And why would we do that? Well, your negatives are electrons, right? And your positives are protons. So to be balanced, you want to have the same amount of positives as you do negatives to balance each other out. That's why. So for sodium, sodium again has that weird symbol of Na. Okay? So it's number 11 on the periodic table. Now, it's got a mass number of 24, and its atomic number at the top of the box, if we're looking at sodium, it's going to have that 11 either here or here in either location. But when in doubt, look at the top of the box. So it's got that 11, which means it's got 11 protons. We said that for today, the protons were also going to equal the electrons, so our positive and negatives were going to be equal. How many neutrons do you have if you are sodium? So if you have a mass of 24, you take 24 minus the 11 protons, which would be 13 neutrons. Because 11 protons plus 13 neutrons will equal 24 for your mass. So that's what you're doing today. You are taking the information that is given to you, and you're going to attempt to identify the missing numbers, okay? So if you have any questions, maybe ask a classmate or feel free to send me an email. And I hope that was helpful. We will check it tomorrow.